Hello guys, we're gonna start a new chapter, which is chapter 8, DC motors and generators. There are four major types of DC generator, classified according to the manner in which their field flux is produced. The first type is separately excited generator, where the field flux is derived from a separate power source independent of the generator itself. The second type is shunt generator, where the field flux is derived by connecting the field circuit directly across the terminals of the generator. The third type is series generator, where the field flux is produced by connecting the field circuit in series with the armature of the generator. The fourth type is compound generator. It is divided into two main sections according to the series and shunt windings connection as follows: cumulative compound generator, differentially compound generator. Cumulative compound, where both a shunt and series field are presented and their effects are additive. Differentially compound, where both a shunt and series field are presented and their effects are subtractive. Here additive and here subtractive. DC generators are compared by their voltages, power ratings, efficiencies, voltage regulations. We have an equation to find voltage regulations. By this equation, VR equal what here? Voltage at no load minus voltage at full load divided by voltage at full load multiplied by 100%. All generators are driven by a source of mechanical power, which is usually called the prime mover of the generator. The prime mover may be a steam turbine, a diesel engine, or even an electrical motor, as we did in our lab. Since the speed of the prime mover affects the output voltage of a generator, and since prime movers can vary widely in their speed characteristics, it is customary to compare the voltage regulation and output characteristics of different generators. Assuming constant speed prime movers in these lectures, a generator's speed will be assumed to be constant unless a specific statement is made to contrary. Section 8.12, the separately excited DC generator. It is a generator whose field current is supplied by a separate external DC voltage source. The equivalent circuit of such machine is shown in figure 1. As we can see here, this is the I field. Okay, this is V field, and this is the resistance with the inductance field, and this is here EA armature voltage. This is the symbol for the armature with the brush. We have IA, armature current, and RA, armature resistance. And we have equations also here. I load, this is I load, will equal what? IA, armature current. And VT terminal, V terminal here, V terminal is here equal EA minus IA multiply RA. In this circuit, the voltage VT represents the actual voltage measured at the terminals of the generator, and the current IL represents the current flowing in the line connected to the terminals. The internal voltage is EA, and the armature current is IA. We have also these equations. EA equal what? K flux omega. Flux density per meter square, and omega generator speed rad per second. This is the unit for omega. It is clear that the armature current is equal to the line current in a separately excited generator. The terminal characteristics of a separately excited DC generator. The terminal characteristics of a device is a plot of the output quantities of the device versus each other. The output quantities for a DC generator are its terminal voltage and line current. The terminal characteristics of a separately excited generators is thus VT versus IL, or simply VT versus what? IA, for a constant speed omega. By Kirchhoff's voltage law, the terminal voltage is VT equal what here? EA, armature voltage, minus IA multiply RA, armature current multiply armature resistance. Since the internal generator voltage EA is independent of IA, the terminal characteristics of the separately excited generator is a straight line, as shown in the figure 2. And this is an ideal case. However, when the load supplied by the generator is increased, IL, and therefore IA increases. If the load supplied by the generator is increased, IL will increase. As the armature current increases, then the IA-RA drop increases. So the terminal voltage of the generators falls. Moreover, in generators without compensating windings, an increase in IA causes an increase in armature reaction, and armature reaction causes the flux weakening. This flux weakening causes a decrease in EA, which further decreases the terminal voltage of the generators. The resulting terminal characteristics is shown in the figure 2. This is the figure here, the terminal characteristics of separately excited DC generators. We have A with compensating windings, which eliminates the armature effect, and B here without compensating windings. This is VT in Y axis, and this is IL in X axis. And we can see that we have EA. This is ideal case, constant. It will goes down the armature reaction. So in summary, we can just make a summary for at no load and with the load. At no load, IL equal IA equals 0, VT will equal EA. With the load, here IL equal IA increase, so here the drop will increase, the VT will goes down, false. With compensating windings, armature reaction here increase, flux will decrease, EA will decrease, VT will goes down. This is in summary with the load and without load. How we can control the terminal voltages for this type of generators? The terminal voltage of a separately excited DC generators can be controlled by changing the internal generator voltage EA of the machine by Kirchhoff's voltage law. This is, we have the same equations here, VT equal EA minus IA RA drop. If EA increases, VT will increase, and if EA decrease, VT will decrease. Since the internal generator voltage EA is given by equations EA equal K flux omega, then there are two possible ways to control the voltage of these generators. Two ways we have. The first one is changing the speed of rotation, and say the second one, changing the field current. Changing the speed of rotation, if omega increases, then EA increases, so VT increases too. This is the summary here. Omega increase, EA increase, VT will increase. Changing the field current, if RF is decreased, then the field current increases. Therefore, the flux in the machine increases as the flux rises. The EA, omega must rise too. So this is the summary again here. We can summarize this one. RF increase, IF decrease, flux decrease, EA decrease, VT decrease. If RF decrease, then IF increase, flux will increase, EA increase, and VT increase. In many applications, the speed range of the prime mover is quite limited. So the terminal voltage is most commonly controlled by changing the field current. The equivalent field current of a separately excited DC generator is given by IF equal what? IF minus armature reaction over NF. Also, the difference between the speed of the magnetization curve and the real speed of the generator must be taken into account using these equations here. EA over EA 0 equal the speed over speed 0. This is the separately excited DC generators for the example 8, 9. We're gonna start to solve the example 8, 8.9. Example 8.9. A separately excited DC generator is rated at 172 kilowatt, 430 volt, 400 ampere, and 1800 revolution per minute. It is shown in the figure 8.47, and its magnetization curve is shown in the figure 8.48. This machine has the following characteristics. We have RA 0.05 ohm, RF 20 ohm, R adjustment from 0 to 300 ohm, VF 430 volt, NF 1000 turns per pole. A, if the variable resistors are adjustment in this generator's field circuit is adjusted to 63 ohm, and the generator's prime mover is driving at 1600 revolution per minute. What is this generator's no load terminal voltage? We have to calculate the terminal voltages. Okay, so this is the figure for the machine here. As we can see, this is the EA armature, okay, voltage, and RA armature resistors 0.05. We have IA armature current and I load. IA will equal I load, and this is V terminal, okay, and this is VF field voltage 430 volt, and this is our adjustment here from 0 to 300. This is resistor we can variable resistors we can vary the value. This is RF 20 ohm, and this is LF number of turns 1000 turns. Okay, this is the separately excited generators, and this is the curve here. As we can see, we'll find some values from this curve. Okay, now we'll solve part A to find terminal voltages. If the generator's total field circuit resistance is, we have to add RF plus R adjustment, so the total will be 83 ohm. So the field current in this machine is IF will equal VF over RF, Ohm's law. Okay, so 430 volt over 83 ohm. So the answer will be 5.2 ampere. From the machine's magnetization curve, this much current would produce a voltage EA O. How much here? 430 volt. At speed 1800 revolution per minute. Since this generator is actually turning at speed, this is the speed here, 1600 revolution per minute. Its internal generated voltage EA will be, we can use this formula now, EA over EAO equal NM speed over NO. Okay, guys. Now, I multiply here both sides here. So EA EA equal what? 1600 over 1800 revolution per minute multiply 430 volt. So the answer will be what? 382 volt. Okay, since VT equal EA at no load, VT equal EA at no load conditions, the output voltage of the generator is VT equal what here? So VT will be equal 382 volt. So this is the answer for part A. So let us check the graph here for this point, how we can get this value from the graph here. Okay, we get 5.2, so we can go back to the graph here. Here 5.2, this is 5.2. If we go up here at this point here, how much the voltage? It will be what here? 430. Okay, so when we calculate the currents for 5.2, we can go to check the graph and find the value here, 430. Okay, now part B, what would its voltage be if a 360 ampere load were connected to its terminals? Assume that the generator has compensating windings. Okay, now B, okay, so if a 360 ampere load were connected to these generators terminals, the terminal voltage of the generator would be, we can say that VT equal EA minus IA multiply what? RA. Okay, multiply what here? Yes, RA equal here. So substitute the value EA, we have 382 minus 360 ampere multiply what here? RA, we have 0.05 ohm. So the answer will be what here? 364 voltage. So this is the answer. Okay, guys. Now part C, what would its voltage be if a 360 ampere load were connected to its terminals, but the generator does not have compensating windings? Assume that its armature reaction at this load is 450 ampere per turns. Okay, now for C, if a 360 ampere load were connected to this generator's terminals and the generators had 450 ampere, turns of armature reaction, the effective field current would be, we can say that if effective equal if equal what here, guys? If minus armature armature reaction over NF. So substitute the value 5.2 ampere, okay, minus 450 ampere over number of turns here for the field, 1000 turns. So the answer would be 4.7775 ampere. So from the curve EAO will be 410 volt. We can take this value ampere and check the graph. We'll see the value how much here, 410 volt. So the internal generated voltage at here speed 1600 revolution per minute, okay, would be what we can use the same formula here, EA over EAO equal what, N over NO. This is the speed. Now EA equal what here, guys? 1600 over 1800 multiply 410 volt. We get the answer 364 volt. Therefore the terminal voltage of the generators would be, we'll substitute the equation for the generator, VT EA minus, because we are talking about the generators, okay, IA multiply R multiply RA equal here, substitute the value EA 364 minus 360 multiply RA 0.05. The answer will be what here? 346 volt. It is lower than before due to the armature reaction, because the effective armature reaction VT goes what here? Goes down. Now D okay, what adjustment could be made to the generator to restore its terminal voltage to the value found in part A? So the voltage at the terminals of the generators has fallen. So to restore it to its original value, the voltage of the generators must be increased. This requires an increase what in EA. We have to increase in EA, which implies that our adjustment must be decreased. Must be what? Decreased, to increase the field current, to increase the field current, okay, of the generators. Okay, so we have to increase EA. So our adjustment should be decreased to increase what? The field current. This is D. This is part D. Okay. Now, the last part for this example here, E. How much field current would be needed to restore the terminal voltage to its no-load value? Assume that the machine has compensating winding. What is the required value for the resistors adjustment to accomplish this? Okay, this is now E. For the terminal voltage to go back up here, 382 volt, the required value of EA, okay, is what here? EA equal VT plus IA multiply RA. Substitute the value here, guys. 382 plus what? 360 multiply RA 0.0 what here? 5.05. So the answer here 400 watt volt. To get a voltage EA of 400 volt at the speed here 1600 revolution per minute, the equivalent voltage at the speed at 1800 revolution per minute would be what? Again, we'll use the same here equations. EA over EAO equal what? The speed motor over the speed O. So EAO equal what? 1800 over 1600 multiply 400. The answer will be 450 volt. From the magnetization curve, the voltage would require a field of IF 6.15 ampere. We take the value 450 volt and check to get the current, the value of the current here. The field circuit resistance would have to be what? RF plus R adjustment equal what? VF over IF. RF 20 plus R adjustment equal here 430 over 6.15 ampere equal what here? 69.9 ohm. So R adjustment, just move 20 to the another side here. So R adjustment will be what here? Subtract 20 from the value 69. It will be what? 49.9 ohm. So approximately it will be what here? 50 ohm. Notice that for the same field current and load current, the generator with armature reaction had a lower output voltage than the generators without armature reaction. So this is the end of this example 9. Section 8.13, the Shunt Dc Generator. The shunt DC generator is a DC generator that supplies its own field current by having its field connected directly across the terminals of the machine. The equivalent circuit of a shunt DC generator is shown in the figure 4. In this circuit, the armature current of the machine supplies both the field circuit and the load attached to the machine. We have IA equal what? IF plus I load. Armature current equal field current plus the load current. The Kirchhoff's voltage law equations for the armature circuit of this machine is what here? Vt equal EA minus IA multiply RA. And this is the equivalent circuit for the shunt DC generator. As we can see here, RF with RLF is connected across what here, or directly or parallel to what? RA or armature here. This is RA with EA armature here. This is parallel here, and we have VT terminals. This is the equations. Very important to know the equations for this machine. IF equal here VT over RF, and we have IA equal IL plus IF, and VT equal what? EA minus IA multiply RA. And IL here we have equal what? VT over RL. This type of generator has a distinct advantage over the separately excited DC generators in that no external power supply is required for the field circuit, but that leaves an important question unanswered. If the generator supplies its own field current, how does it get the initial flux to start when it is first turned on? Voltage build up in Ashant generators. The voltage build up in a DC generator depends on the presence of a residual flux in the poles of the generator. When a generator first starts to turn, an initial voltage will be generated, which is given by EA equal K flux residual multiply omega. This voltage appears at the terminals of the generators. It may be a volt to 5 volt. A volt to what? To 5 volt, which is very low value of voltage. But when that voltage appears at the terminal, it causes a current to flow in the generator's field coil. IF equal VT over RF. This field current produces a magnetomotive force in the poles, which increases the flux in them. The increase in the flux causes an increase in armature voltage, which increases the terminals of voltage, VT. When VT rises, IF increases further, increasing what? The flux more, which increases EA, and so on. So see the figure 5. This is here figure 5. Build up voltage process here. First, it starts with just a residual flux. This is with a residual flux. Then B, as the flux increase because the current, then EA increase. Okay, EA here will increase. For C, EA will reach its rated value with the increase of the current. Okay, we have now flux 2. Here it is flux residual, then flux plus here flux 1, then flux plus flux 1, flux 2. Okay. What if a shunt generator is started and no voltage build up? What could be the wrong here? There are several possible causes for the voltage to fall to build up during starting. Number one, there may be no residual magnetic flux in the generator to start the process going. If the residual flux 0, so then EA watt will be also 0 here, and the voltage never build up. If this problem occurs, disconnect the field from the armature circuit and connect it directly to what to an external DC source, such as a battery. This current follow from this external DC source will leave a residual flux in the poles. Number 2, the direction of the main magnetic flux in the opposite direction of the residual flux. There are two possible reasons for this case. A, the direction of rotation of the generators may have been reversed. B, the connection of the field may have been reversed. In either cases, A or B, the residual flux produces an internal generated voltage EA. The voltage EA produces a field current which produces a flux opposing the residual flux instead of adding to it. Under this condition, the flux actually decreases below the residual flux and no voltage can ever build up. If this problem occurs, it can be fixed by what? By reversing the field connections, by interchanging the terminal of the shunt winding terminals. Number 3, the field resistance may be adjusted to a value greater than the critical resistance. If the additional shunt field resistance has a large value, then the voltage of the generators can fluctuate very widely with only teeny change in RF or IF. This value of the resistance is called the critical resistance. If RF exceeds the critical resistance, then the steady state operating voltage is essentially at the residual level and it never build up. So what is the solution here? The solutions of this problem is to reduce the value of the variable resistance. So very important, guys, here you have to know each problem and the solution for each problem. Terminal characteristics of a shunt DC generators. The terminal characteristics of a shunt DC generators differs from the separately excited DC generators because of the amount of field current in the machine depends on its terminal voltage. So we have at no load, okay, the armature current will be equal to the field current and the voltage build-up process is assumed finished. In this case, the VT of the generators is built and equal to VT. We can notice that VT of the shunt generators at no load is what? Less than VT of the separately generators at no load. As the load of the generator increased here, IL increases, and so IA will increase also. An increase in IA increases the armature resistance. Voltage drop causes VT to decrease. Okay, we can check the points here. Okay, in the graph here. This is the summary here. You can check the summary. It will be very easy for you guys. At no load, IA equal IF, VT equal what here? EA minus IA multiply RA. With the load, increase, IL increase, IA will go increase, IARA drop increase, VT decrease, IF decrease, flux decrease, EA decrease, VT will decrease. Okay, this is the graph. Determine characteristics here of the shunt. This is the graph here with the characteristics of separately. This is the VT and this is the IA here. This is the ideal case. Okay, as the current increase here. This is the separately and the shunt here. Okay, this is for shunt and this is the separately excited. This is the ideal case, be straight line. So the voltage will not goes down for ideal case. Voltage control of a shunt DC generator. How we can control the voltage? How we can control the voltage here? As with the separately excited generators, there are two ways to control the voltage of shunt generators. One, change the shaft speed of generators. Two, change the field resistors of the generator, thus changing the field current. Changing the field resistor is the principal method used to control terminal voltage in real shunt generators. If the field resistance RF is decreased, then the field current IF will what here? Decrease, or sorry, will increase here. When IF increase, the machine flux increases, causing the internal generators EA to increase. The increase in EA causes the terminal voltage of the generators to increase as well. This is here. We can see this. Okay, the summary. When RF increase, IF will decrease, flux decrease, EA decrease, VT what decrease. When RF here decrease, IF increase, flux increase, EA increase, VT increase. Problem 3. Let us solve example for the shunt DC generator now. A shunt generator delivers a load current of 450 ampere. This is IL at 230 volt. 230 volt. This is what here. This is VT, V terminal. Okay, and the resistance of the shunt field and armatures 50 ohm and 0.03 ohm. Okay, this is here. This is RA and this is what RF. Always RA will be what with the low value, like 0.05, 0.03. Okay, calculate the induced voltage or calculate the EMF, electromotive force, the induced what voltage. Now let us calculate. This is the circuit, by the way. This is the circuit for the shunt here, EA. This is the parallel. Okay, RF. Okay, with here this is the VT. Let us solve the example. first we have to find what I field current here, VT over what, over RF, 230 volt over what, 50 ohm. The answer will be 4.6 ampere. Okay, now IA, we have to find IA. IA equal what? IF plus what? I load. 4.6 plus what? Plus 450 ampere. IA will be what here? Will be 454.6 ampere. Then VT equal what? EA, armature voltage, minus IA multiply what? RA. We need what to find what? Find EA. Okay, generated voltage here, or armature voltage. So EA equal what here? Equal VT. We'll just move to the other side here. VT plus what? IA multiply RA. Substitute the values here, guys. So VT we have 230 plus multiply here 454.6 multiply 0.03 RA. So the answer will be what? 243.64 watt volt. This is the answer for this question.